and what is happening in practice, and some of the techniques and tools that you can use to help facilitate this process. I'm having trouble here with this. Let's just make sure this moves. That's better. So just before we do start, I want to talk a little bit about exida, just in case you don't know who exida is. We've been around for 16 years now, and we specialize in the functional safety arena, cybersecurity for industrial control systems, and alarm rationalization. We've been helping companies worldwide with their automation and safety requirements, and we have offices around the world. The two main offices, one is in Germany and the other one is in the US, in the Philadelphia region. Exida does provide services which are actually what we like to call industry agnostic. In other words, we can go across a number of industries. So we work in the automotive, we work in automation, and we work with the process industries, we work with the nuclear industry. So there's a number of different types of industries that we work with. And within that, we work with manufacturers to provide them with support, management support for their safety side of things, development support, so we can provide hardware and software, consultation for designing safety products. We can also do certification. We have a separate certification company, and we provide tools to help, software tools to help with that process. We also help system designers with their functional safety management setups, to do SIL verification, and also to provide tools. Exida does have the world's leading tool for Safety Lifecycle called Excellencia, which is a suite of tools that goes all the way through from doing PHAs to LOPAs to SIL determination, SRS, SIL verification, and even to look at cost-benefit ratios as well. For the end users, we can help with SIL and device selection, and of course SIL verification, and tools to help with things like the operation and maintenance side, as we shall see a bit later on. And then for the engineering contractor, we provide the tools again, but we also handle competence development. This is another specialist area for Exida, with the certification of personnel, and we have our certified functional safety expert and professional certification programs. We've just introduced a new one for functional safety practitioner, which is a little lower level, but nonetheless has value in improves competence. From a reference material point of view, we've authored a lot of industry books on safety and reliability, and we have the Industry Data Handbook on Equipment Failure. This is known as the SERH, which is the Safe Electrical Reliability Handbook, which is now up to 4 volumes, and the latest edition is coming out pretty soon. So we have all of these books available through the website, and we do supply, when we do our training courses for the functional safety engineering, we do supply 3 of the books that you see here: the Practical SIL Target Selection, the Safety Instrumented Systems Verification, and also the Certified Functional Safety Expert Professional Exam Preparation, which is shown down here at the bottom. In terms of certification, we are ANSI accredited, which means we are a certification body. ANSI is the US accreditation body, and there is a number of accreditation bodies around the world. In the UK, I believe it's COMA, but I wouldn't, or it used to be the HSE. I'm not sure if it still is. But from the products, personnel, processes and procedures side, we have, as I mentioned earlier, an independent certification company that deals with that. We do product certifications for both cybersecurity and functional safety, and we've actually certified more devices than anybody else in the world today. Exida is accredited, as said, by the ANSI, the American National Standards Institute here in the US, and we have what's called this A-class accreditation. little bit about me. I'm the VP of Global Business Development. I have 38 years experience in industrial safety and controls. I joined ICS in the early 80s. ICS was Industrial Control Systems in services in the UK. We pioneered safety systems back then based on microprocessor technology, and some of our installations that were done back then for the ICS 2000 and FGS 2000 are probably still in service in some parts of the world today. So I was a development engineer back then. I have a CFSP, Certified Functional Safety Professional. In fact, I do a lot of the training for exida for the functional safety side of things. Member of the Association of MBAs and the ISA, and I published a paper on managing risky projects, which was basically developing a product for the safety systems market. And of course this IEC 61511 O&M requirements. So with that being said, let's start off with a little background, little introduction. Some of you may be aware of the standards that exist. There's what's known as the base safety standard, which is actually the IEC 61508. It was developed specifically for manufacturers of safety equipment, such as logic solvers and sensors, final elements, etc. But that was also then used as the basis to provide what was known as sector standards. And in 2003, the IEC 61511 standard was issued for the process industries as a sector standard. And as you can see there are two more, but actually there are three more, because now there's one for the automotive, which is the IEC 26262. These standards are unique in such that they are not prescriptive. They don't tell you how to do something. They tell you what needs to be done, but they don't tell you how to do it, because they're performance-based, and they're based around a safety life cycle. Since its inception, the IEC 61511 has been widely adopted by companies all over the world operating in process chemical, petrochemical. In fact, anything that has hazardous, potentially hazardous processes would need to conform to this. The emphasis of the SLC, the safety life cycle, is on risk and risk mitigation, reducing the potential for hazards that could lead to the loss of life and destruction of property. I mean, that picture that you see there is from Piper Alpha, which was the worst North Sea disaster that happened in 1988, and was the result, unfortunately, of many things, but not least of which was maintenance issues with the fire and gas system. They were having problems with gas detectors, and they basically had them inhibited so that when the gas leak occurred, the fire and gas system couldn't detect and couldn't take action. So it's very important that the safety instrumented systems are properly maintained during their lifetime, and that's where this particular presentation today is focusing. If we look at the safety life cycle from 61511, it's very similar to the life cycle in 1508. Basically, there are three phases. There's the analysis phase, the realization phase, and the operation phase. And as you can see here, what we are looking at is the clause 16 for operation and maintenance, but there's also modification under clause 17. Now, the whole point of this is if we don't follow the proper operation and maintenance procedures, perform the proof tests that we need to perform at the frequency we need to perform that, do not measure and monitor the performance of our safety instrumented system, then everything we did in the analysis and realization phase is for nothing, because you will not achieve the reliability and protection that you're looking for from your safety system. If we look at it in a little more detail, what we're looking at is we need to have operation and maintenance plans and proof test procedures, because what we need to be able to do is to keep proper maintenance records and to record proof test results. It's very important. Remember, this is a performance-based standard. It's not prescriptive. So we need to be able to measure and to see how we're doing with the performance of our SIS. And here again, the standard doesn't say how often you need to do that. It says it needs to be done on a regular basis. So let's look at clause 16 in a little more detail. So for a start, it requires that you have a properly and well-defined operation and maintenance plan. In other words, how are you going to ensure that the SIS can achieve the desired performance for its particular lifetime? This will include all tests that you need to verify the proper operation of the safety instrumented functions. Now remember, a safety instrumented system will consist of one or more safety instrumented functions. And safety instrumented functions themselves consist of a combination of sensors, logic solver, and final element. So the particular equipment within the safety instrumented function will be defined within the safety requirement specification. And for each safety instrumented function, there will be a defined series of proof tests and also the frequencies that these proof tests need to be run. So the periodic test interval that was calculated during the SIF verification has to be documented as part of the plan. So this means that when you do your calculations, you are basing it on a particular coverage factor for the proof test. In other words, how many dangerous faults potentially can we find with our proof test? And also, how often do we need to run it? So the other thing to remember is that each SIF will have potentially different proof test intervals for the pieces of equipment that they have. And that needs to be recorded and that needs to be followed. So what we need to do is develop a kind of safety checklist. As with the safety requirement specification, the O&M plan is a working document. So the purpose is to ensure that each SIF of the SIS is maintained to meet its design safety integrity. So what does that mean? Well, it means we need to understand what are routine and abnormal operation activities. We have to perform the proof testing. We need to look at preventative and breakdown maintenance. We need to have procedures, measures and techniques to be used for the operation and maintenance and verification of adherence to O&M procedures. There was the case in the Texas City incident back in 2005 where the explosion was a result of several different things, but not least of which was not following their own procedures, who violated their own procedures. So it's important that these are followed. It's important that they do happen, because that was another thing. Records showed that they were saying that maintenance was performed on certain equipment when it actually hadn't been. And the persons, departments and organizations responsible for these activities need to be defined. The standard says that you need to be competent to work on the particular stage of the life cycle you're working on. It also says that people need to be made responsible, and they need to identify who is responsible, and these people need to be trained so that they can make sure they follow the procedures and do things correctly. So what you need to do is create procedures for each of these and make sure they're maintained, especially following updates and modifications to the SIA. The other thing I like to say when I teach the safety course is I use the expression RTFM, which means read the flaming manual, because the manufacturer's safety manual needs to be followed. Otherwise, you will not end up getting the optimum performance from the particular equipment. The manufacturer's safety manual will, in most cases, give you some suggested proof tests that you can follow and also suggest the period of time and how much coverage. They will also tell you what the useful life of the equipment is. Now here again, if the manufacturer says the useful life of the equipment is 5 years, some companies will have a policy where they say if the equipment hasn't failed by the beginning of the 5th year, then you replace it regardless. Others will say, well, we have a run to fail policy, so they'll keep running as long as they can. There's risk with that, of course, but at the end of the day, the end user has to accept that risk. So if you take this approach, then you can use it rather like a safety checklist. The other example I give when I teach the course is that, for example, pilots may have flown thousands of hours, but every time they get in the cockpit, they follow their startup checklist. They don't rely on their memories, they always follow, so they have a systematic approach to ensure that they do things correctly. So what about the operation and maintenance procedures? Well, 16.2.2 says that you need to have these developed such that routine actions required to maintain the as-designed SIST are achieved. So what does this mean? Well, that will talk about how often you need to do the maintenance and how thoroughly. Actions and constraints to prevent unsafe state during maintenance. Obviously, if you're going to be doing maintenance, then if you're doing it on a live system, you've got a hot permit system in place, you need to make sure there are proper safeguards to ensure that there aren't going to be any dangerous situations occurring. The case in the Texas city was during a startup. There was an incident to Sorrow where they had done some maintenance on some heat exchangers and they were doing a startup when it blew up. So clearly maintenance and starting up are very critical periods of time where you need to make sure that you are diligent and have everything in place to ensure that there can't be an incident. Information needs to be maintained on the system failures demand rate. Again, we're looking at the performance. So if, for example, the SRS said that the spurious trip rate shouldn't be any more than once every 24 years, and yet in the first year we're having 3 or 4 spurious trips, we need to understand why that is. So there needs to be a mechanism for documenting that and a mechanism for investigating. Information to be maintained from audits and tests. Once you've done the testing, you need to make sure you record the results. But here, you need to make sure you record the as found and the as left conditions, and the maintenance people need to be trained to be able to do that. Procedures to be followed when failures occur with the SIS. What happens then? What do we need to do? And the test equipment used obviously needs to be calibrated. That's another thing that often happens, is that equipment that's used for setting up field devices sometimes is not calibrated. So let's look at procedures to be followed when faults or failure occur with a SIS. So, okay, procedures for fault diagnostic and repair. If a diagnostic comes up and says that there is a potential problem, it needs to be addressed. So what do you do then? What are the procedures to go through? What procedures are there for validation? Once you've done the repair, you've got to make sure you validate the loop again. The procedure has to, or the standard says that you need to, if you make any changes, you need to ensure you haven't compromised the integrity of the safety instrumented function. So that means going back and redoing the calculations. And I know that this doesn't happen that often, because maintenance people have enough to do and they don't get time, but it needs to be addressed. It's usually the responsibility of the plant safety manager or the mechanical integrity program manager. Procedures for tracking performance have to be in place. And like I said, test equipment used during maintenance is calibrated and up to date. From the O&M Personnel Competency side, standard 16.2.4 says they need to understand how the SIS functions in terms of normal functions and abnormal functions. What's the hazard the SIS is protecting against? What are the operation of all bypasses, and when and how do they need to be applied? So, for example, permissives for startup. what happens when you shut down. Operation of any manual shutdown switches and startup switches. What action is required upon any SIS diagnostic alarm? They need to be trained in how to do that, and they need to understand what this particular safety instrumented system is protecting against, or the hazards it's protecting against. So they need to be trained to sustain the full performance of the SIS. And there's a number of ways you can do that, of course. They need to follow proof test procedures. Proof testing is very important. Clause 16.2.8. The purpose of a proof test is not to prove that the equipment works. The purpose of a proof test is to try and find potentially dangerous faults that could cause a failure on demand. That's the whole point. So in terms of competency for the O&M people, they will need regular training. You will need to do some competency audits and assessments. So this would be for new and all updated components. For example, every 10 or 12 years or more, you may go through a full change out of the SIS. Or you may be replacing some of the automation, the BPCS, for example. So they need to be trained and need to understand what's happened, what's changed, what's old, what's new, that's left, and which components are being replaced. So training records and assessments need to be kept for the auditing purposes. Some companies will keep a matrix. Basically, it's an Excel spreadsheet where they'll have the personnel listed, and then they'll have particular competencies across the top, and they'll indicate whether they've been partially trained, fully trained, or they're regarded as being experts. So what happens in practice? Well, the end users are actually responsible for enforcing this, and that can be good or bad, because it will depend upon the culture. If the organization has a good safety culture, they'll make sure that personnel are trained properly and understand, and they follow procedures. If they have a checkbook mentality and they're only worrying about reducing cost, then you know the corners are going to get cut. And that's where the potential for disaster comes in. So the end users have to ensure that adequate procedures, as well as adequate documentation and tracking, is in place. They have to record the spurious trips and actual process demands, as well as any failure events, audit results, proof test results, etc. Basically, the performance of the system. And it will require that the O&M personnel be diligent in recording the required information. That is another challenge. I have spoken to O&M people who say that they don't have the time to properly do things. That is not a good situation. So it needs to be done. Clause 16.28 says you require a proof test procedure to be developed for every piece of equipment in a SIF to describe correct operation and correct diagnostic alarm and indications. As I've already mentioned, most manufacturers of certified products for safety applications will have in their safety manual a suggested proof test procedure and a coverage factor. And this needs to be adhered to. Also, you need to do visual inspections as part of the proof test. So it's not just a mechanical or electrical test, it needs to be a visual. So if you have an infrared instrument that has a window, you need to make sure that's clean. The valves, for example, they need to be looked at to make sure there's no signs of corrosion, the piping as well. There was an incident at a Chevron plant a few years ago where a pipe burst because it was so badly corroded it couldn't take the pressure anymore, and it gassed some employees. Now, if they had been doing visual inspections, they would have seen that pipe was badly corroded, but they didn't. So proof test intervals, these need to be carried out as specified in the SRS. The mean time to restore is specified for each SIF in the SRS, and that needs to be followed. If not, then again you are compromising the integrity of the SIF. And that means your reliability is going to be less. So personnel need to be regularly trained and assessed to make sure that if it says that mean time to restore is 48 hours and it's taking 72 hours to repair things and get them back up and running, there's a problem, and that needs to be looked at. The standard says that you do need to do an impact analysis and analysis report every time you make a change, because from the SIF's point of view, if you're changing components, you need to make sure that it hasn't compromised the integrity of the SIF. There have been instances where a sensor has failed. The maintenance people have gone in, they've looked in the stores, they've found another sensor, they've gone, replaced it, and without knowing it, they've completely compromised the SIF, because instead of using a certified sensor, they went in and took a generic sensor and put it in. So that's another thing that has to be guarded against. So how is data recorded? That's the next thing. 16.3.3 says the end user must maintain records that certified proof tests and inspection were completed. This needs to be part of the audit trail. And as I've said already, proof tests are to detect faulty equipment prior to a demand being placed on the SIS. It's looking for dangerous undetected faults and trying to reveal them. That's why the coverage factor and the frequency is very important. The records need to include a description of the tests and the inspections performed, the dates of the tests and inspections, the name of the person who performed the inspections, serial number, unique identifier of the system tested, for example, what's the loop, what's the SIF, etc., and what are the results. And this is important that the as found is recorded, as well as the as left conditions. As I've mentioned already, the standard does not define how these results are recorded. It just says you need to record them. And most records right now are either paper or some form of Excel spreadsheet. I was talking to a customer a little while ago, and he was saying that they have to scan all their reports for their SAP system, and it takes a significant amount of time, and they were getting behind in doing that. Now what happens is if people get busy and they get sidetracked, these things won't get done. So it's very important, and this is where technology can help. If you have a software-based tool or handheld or tablet device, it can save you time and money. The thing about the tool, though, is it has to record functional safety statistics and performance metrics. So if you're going to be looking at complying with the requirements of Clause 16, you've got to record the demands that are placed on the SIS, both real and spurious. As I mentioned already, if your SRS specifies that the spurious trip rate is once every 24 years or 25 years, but you're seeing a lot more frequent spurious trips, that requires investigation. Inspection and proof test results have to be maintained, and of course maintenance activities themselves. If you're doing calibration, if you're doing changes, whatever. And failure reporting. If there are faults, how are we reporting those faults? The other thing to look at is discrepancies between the expected versus the actual behavior of the SIS. That's very important, because as part of the performance, when you do the design, your safety requirement specification, which incidentally has to be a live document, it cannot be just shoved on a shelf and forgotten about. That needs to be followed, and if you're finding that the performance is not coming up to the requirements, then you need to do an analysis and investigation as to why that is. Recording demands on the SIS. You need to do that such that you're able to determine which layer of protection failed. This is important because you may have several layers of protection, not just the SIS itself. There might be a BPCS, the Basic Process Control System. There may be some other non-SIS related layers of protection. But you need to know if those layers failed, you need to know they failed. You need to know why they failed. Also, you can look at the demand frequency and compare that to what was determined during the hazard scenario, the hazard analysis. Generally, what happens is once you've done your hazards, you've identified your scenarios, you've gone through, you've looked at your LOPA, your layer of protection analysis, and you've come up with a residual amount of risk that you want to reduce, then you design your SIFs to reduce that risk. That's where you determine whether it's a SIL 1, a SIL 2, or a SIL 3. So clearly, if the demand frequency is different from what was originally anticipated, then you need to go back and analyze and look at why that is. This means discrepancies between the expected versus the actual behavior of the SIS will need to be analyzed and looked at, especially if there are any modifications. And this is governed under clause 16.2.6. Here's an example of a tool that can do this. This is the SILSTAT tool. For example, here you see there are 5 independent protection layers, and you can see in this case the low firebox pressure alarm was successful. So you can see which protection layer was successful, and you can use that information to look at the demand frequency of the hazardous event. Is it occurring at the expected rate? In this example, you can see that 3 layers have failed, but the 4th one was successful. So again, this would suggest that we need to look at why those 3 layers failed. What was the problem? You can record hierarchy for the plant as well. So you could be global. In this instance, we're showing that this is in the US, in Philadelphia. It's a heat recovery steam generator. We're looking at the heater burner and this particular tag number. And you can see here, you've got the devices that you could store and identify the tags and descriptions, etc. So the tool can be linked to, for example, stores area. So you can see if you have any devices in stock that you can use to replace. It's a useful way of doing that. It saves time and will improve your efficiency. So here again, if you're looking at the devices, in this particular example, we're looking at a Rosemount pressure transmitter. It's a 3051S. There's the serial number, and you can see we have a series of these devices down here. It gives the manufacturer, it gives the model number, it gives the serial number. And then you can record where it's located, etc. Is the device active? Is it being repaired? Is it out of service? Etc. So this will help the O&M people carry out effective maintenance and or replacement. From the proof test generator point of view, you can include the proof tests here in the tool. You have basically the pass-fail criteria, and then you can record the particular device, what was the revision number, what was the date, is the proof test active or not. So you can have different proof tests for different devices, as we said already, because each SIF will have different equipment on it, which will have potentially different proof test requirements and proof test intervals. So the tool like this can help you with running those tests, and it will remind you when these tests are due. And as we've said already, proof testing is essential for ensuring the SIS integrity. Recording results. You can record the results that you have here. There's a comment field. There's a field value. So if you have a smart transmitter and you're looking for a particular value in terms of the current, you can actually record what you found in the field, and you can put a comment and say whether it was good, passed, or not. So you can record the as found, and you can record the as left conditions. So for maintenance activities, you can see here that you have different types of maintenance that you'll be doing. You could be doing a reset, clean, recalibrate, repair, commissioning. You could be dealing with a loss of containment, startup or shutdown. Any particular situation, you can record that particular activity. You can record the device that you were looking at or devices you were looking at, and you can record what you did. So here we have a condition-based maintenance activity going on. There's a hissing sound at the actuator, and it's a minor seal leakage in the spring chamber, potential for becoming a large leak and fail-safe. So you can very quickly locate the device, and you can record the as found and as left condition, as I said, and then you can go to the stores and see, do you have a replacement part or not. From the event point of view, you can see here we can record events. We can use colors to indicate potential problems. You can see here that the top one was a proof test, which was fine, but the second one down below, we have a tightened flange, and there needs to be some preventative maintenance on that one. And you can look at it in terms of the time and assess any implications or further actions to be taken. So again, this is helping you look at the performance of the system. So what are the key benefits of being able to use an automated recording system? Well, you can do detailed analysis of failures because you can look at specific addresses, devices, and device types. You can even look globally if you had this network. You get the frequent benefit of reducing false trips because if you see things need attention earlier rather than them failing and causing a false trip, that will help reduce the frequency of false trips. You will have the ability to compare the actual versus expected performance. In the case of SILSTAT, you can actually upload to the Excellencia tool the information to redo the SIL verification calculation. And vice versa, if you do the design in Excellencia, you can export that into SILSTAT so that SILSTAT has all the equipment for each SIF that was done in the design. So it's automatically populated. You have the ability to ensure your risk reduction is adequate, because obviously if you're looking at your actual versus your expected and you're saying, yes, it's roughly where we expect it to be, so we're okay. Or you may find that it's not adequate. We're actually getting a much poorer performance. That enables you to go back and do some assessments to look at why that is. If the reduction is more than adequate, then you might be able to do some modification to simplify the design a little bit, and which will reduce the cost and make maintenance a lot easier. So it can help you provide data for future lifecycle tasks, such as when you go back and redo your HAZOPs, your risk assessments, your LOPA, your SIL target selection, and your SIL verification. Every 5 years, most companies go back and redo their HAZOPs and LOPAs to make sure that things haven't changed or deviated significantly, or if there's been a change in performance. You can reevaluate the frequency of your proof tests, and it'll help communication between the plant departments such as operations, maintenance, process safety, reliability, and engineering. So you're all working from a common set of information. So let's look at this then in summary. The whole point is that you need to manage risk. You can't ignore it. And so you need to adopt an appropriate safety-first culture. This means that you have to have trained and competent operation and maintenance personnel to make sure that they keep the SIS performing the way it was designed and intended to perform. That you have proper operation and maintenance procedures. That you do develop a safety checklist to ensure consistency, and you undertake regular employee competency assessments. If you have a change in staff, if you have some new equipment coming in, you've got to make sure that the employees are properly trained and assessed. Some companies might have simulators, offline simulators for their control systems and SIS. That's great. That gives them a chance to be able to try things out in a fairly safe environment. And above all else, you've got to make sure that you ensure that proof testing is conducted in line with the SRS requirements. That can't be stressed strongly enough. The SRS is a living document. As time goes on, if changes are made to the SIS that are obviously assessed and approved, it needs to be reflected back in the SRS as well. You need to record all maintenance activities accurately and faithfully. It's very important to do that. And that's why the as found as well as the as left is very important to record. You can use software tools to assist in the recording or auditing, and you can use software tools to help analyze failures, fault strips, and actual SIS performance. The standard says you need to periodically assess performance. It doesn't tell you how often that is. And so each end user will have to determine whether that's a 3-year period, whether it's a 5-year period, whether it's less, whether it's more. It's all a question of how well the system is behaving and performing, how much good data you have for analysis. And that's part of the problem. Part of the problem is when failures occur in the field, a lot of times they're categorized as systematic failures when actually they're not. And so it's important that faults are analyzed properly and understood. And that's why it's important to record the as found condition, because that can help with the assessment. I mean, the basic rule of thumb is assume a failure is random until proven otherwise. And in doing this, you will obviously keep your plant personnel and your plant safe by following this operations and maintenance procedure. So that's it. If there are any questions, I would be happy to answer them. Just looking to see if there's any questions here. Okay, there's a question here. Does the software automatically record demands on the system, or is it all manually entered? No, the software will automatically record it. Another question, how do you verify performance and how frequently? Well, I did sort of touch on this. Your performance, if you're documenting everything properly, and for example, if you're using something like SILSTAT, you can actually upload that into Excellencia and use the SIL calculation engine to rerun the numbers to see that the PFD hasn't changed, or if it has, how much has it changed, and make sure the systematic integrity hasn't changed, and that the hardware fault tolerance hasn't changed either. Frequently, like I said, there's nothing in the standard that says how often you need to do this. It just says you need to do it periodically. So it would be a question of judgment in terms of the performance of the system over time. If you've been running for 3 or 4 years without any demands, you might decide to go a little bit longer, or you may say that we're going to do it every 3 years regardless, or we'll do it every 5 years regardless. Another question, you mentioned competency, but how do you assess that? Well, like I said again, the standard says thou shalt be competent. It doesn't say how you do that. There are a number of ways of doing that, of course, and clearly if you go on take one of our courses or get on our certification courses, then that's a way of showing competency. The functional safety practitioner would probably be a good one for maintenance people to do, but there would be regular training sessions that need to be held by the end user on the particular type of equipment. Oftentimes the suppliers will run training courses on their equipment, or the SIS supplier will run a training course on that. But basically competency means that you're able to understand and to be able to maintain and operate the equipment correctly. Okay, what happens if performance is worse than expected? Well, that's an interesting one. And again, what you need to do is there needs to be a committee or a team that would be led by the safety specialist for the plant, who would need to review the data. And you may, and the standard says again that you need to go back to the appropriate phase in the life cycle. So that may mean that you go back to the HAZOP, or you may go back to the LOPA, or you may go back and look at the equipment that was chosen. There's a number of things that you may need to do, but basically you can't just ignore it. You've got to go and have a look and see why that is, and then make any adjustments or changes, and also document what you find. That's the whole point. You need to document what you find. Okay, any more questions? Don't see any more. Oh, sorry, yes, there is no one. Okay. My box is a little small, so I need to, let's go all the way up. Okay, let's have a look. In the UK, things are accredited by, okay, thank you for correcting me. The UCAS is the United Kingdom Accreditation Service, now deals with the accreditation for the UK. And the HSE now is the regulatory body to ensure compliance with legislation. And there's another question here. What are the differences between 61508 and 61511 for maintenance? Well, 1508 deals with the actual manufacturers, so they would be looking at the particular product. 1511 looks at the safety instrumented function, which consists of like I said before, a combination of sensors, a logic solver, and the final elements, and any interfaces in between. So when you're looking at the maintenance, you're looking at proof tests. You have to look at the proof tests for each particular device. And as I've said, the manufacturer will give you suggested proof test intervals and proof test that you can follow to achieve a certain level of coverage. And normally when the designers are looking at designing the SIF, they would have the manufacturer's safety manual, and they would use that information. And normally in the SRS, the extract would be put in there. And of course the SRS can be in a number of documents. It doesn't have to all be in one particular document. It can be part of a safety manual, part of another document that is used. How does the software interface to the SRS to record demands? Do you make slides available? Yeah. Okay, so there can be a link between the software and the SIS, or you have the choice to do it manually as well. So there can be some connection through the network, or you can do it manually. And yes, we do make the slides available from the presentation. What was the name of the software? The name of the software that we have here is called SILSTAT, and if you go to our website you'll see it. Can the software be used to analyze how often an override is applied? Yes, because you should be recording that. What are the differences between, yeah, that's the piece. Okay, so we had some good questions. Any more questions? So, as I said, this webinar is recorded and will be made available. And you can always email me if you have any further questions. My email address is sgandy, that's Gandy, at exida.com, and I'd be happy to answer those. And the slides, as I said, will be made available, and Ali will be handling that. So with that, then I thank everybody. I wish you a very good rest of the afternoon and day. And that ends today's session. Thanks a lot. Bye.